This lesson, I demonstrate the meaning of skew lines, which are lines that are not parallel or lines that do not intersect to a particular segment. In the past, I had only been able to verbally tell students the meaning of skew lines, and I never felt that the students truly had a handle on the concept. Even with the hands-on demonstration using straws and marshmallows, I was not able to show the students what skew lines were because the hands-on model would not stand on its own long enough for me to show them lines that are skew. With the Promethean board, the students can see with my cube how I pull line segments apart to show them skew lines. For example, if we want to show all lines that are skew to AB, we pull the line segments that are parallel to AB, as well as lines that intersect AB. The lines that are remaining are called skew. Once I've shown them this concept, the students come to the board to do other examples. They pick a line segment of their own, and then they find all the lines parallel to that segment and lines that intersect their chosen segment. The lines that are left. In this lesson, I show students how two triangles are congruent by matching corresponding parts. I showed the students how to match congruent angles with each other as well as congruent sides. When the sides and angles match, then a correspondence statement can be written. Students see that triangles have to be rotated, translated, or flipped in order to show matching parts. I start by clicking on Triangle Car. I then rotate the triangle. Flip it across the y-axis. And then translate or slide the triangle to match on top of the other triangle. Then to write a correspondence statement, I name the angles that go together as a pair. As you can see, triangle CAR matches with triangle SOV, since angles C and S go together as a pair. A and O go together as a pair, and then R and V go together as a pair. By matching the angles together, we can also see how the corresponding sides match as well. CA, for instance, pairs with SO, like AR pairs with OV, etc. These are application problems in which the students use trigonometry to find the distance, for instance, the distance to a fire nearby. The students can actually see the triangles being formed from the designs drawn, and it helps them to see how the parts and pieces fit together. The angle of depression, for instance, the 22 degrees, they'll notice that it's the equivalent of the angle of elevation, which is also 22 degrees. The height of the lookout tower is the same as the height of the fire. The students can then see that trigonometry is what can be used next to find the distance to the fire. For instance, they'll take the 22 degrees, apply it here, and using trig, they can find the tangent of 22 degrees is equal to the opposite, which would be 75, over the adjacent, which is the measure that they're looking for. Then they can use their algebra and help them to find the distance of D. I also used a little sound to add interest to the problem. Students had already learned how to show when two triangles were made congruent by showing all 6 parts of one triangle were congruent to all 6 parts of another. Now they have learned that there are other techniques or theorems that they can use called side, 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 angle, side, angle, that in a sense are shortcuts for them not to have to show all 6 parts of one congruent with all 6 parts of another. I have the answers hidden behind the boxes, the color boxes, as you can see on the page, and students are asked if the triangles are congruent, and they have to give me the reason why they think they're congruent, and they can give an answer and then come to the board to reveal whether their answer is correct or not. On this slide, I can show the students how to verify if the points given create a parallelogram. I start by plotting the points. I'll enlarge the font scale. Plot the 4 points. Connect the points. Then we would find the slopes of each line segment by writing on the grid. By finding the slope of all 4 sides, we can verify that this side and this side have the same slope. If these 2 sides have the same slope, then I've noticed that opposite sides have the same slope, which verifies that it's a parallelogram. Finding the slopes of the sides of each one makes it so much easier for the students to visualize. To demonstrate for you how I make a copy of the day's homework assignment and paste it to a flip chart, I start by inserting the disc that corresponds with my textbook. I find the correct page, and I use the camera tool from the toolbar, and I take a camera shot of the day's homework assignment. You can adjust the size as needed. Take a snapshot and you'll find that it pastes inside of a flip chart. You can use the zoom feature and size it down or enlarge it, and use the magnifying glass to scroll across the screen. I can write on the figures, I can erase, and as I go over their homework, I'm able to discuss what they see in their textbook. We can zoom in to see the shapes more clearly as needed. The beauty of this feature is that I'm able to see what they see. The diagrams are the same, and I don't have to recreate the figures by trying to draw the exact shapes. It's a win-win situation. Example of a worksheet I scanned into a flip chart, and the students can verify their answers against mine. These are actually my answers that are in red. I can scroll around the page. The beauty of this is that the homework assignment they had in hand is what they see here, and we can minimize it where they can see more problems at once, and also we can zoom in to larger where we can focus and concentrate on one problem. The other thing that's nice about this is that I'm not redrawing the problems and trying to duplicate it on a piece of transparency to show on the overhead, and the students can see exactly what they were given up on the board.